So thanks a lot, first of all, for the organizer to give me the opportunity to come back to CIRM. It's such a great place, and it's such a great pleasure to be with real people instead of black vignettes in my usual lectures. Just a word of caution as a way of introduction. As Remy said, I'm a physicist. I'm just out of a sabbatical in biology, and I'm going to be talking about machine learning on graphs. So that tells you two things, two very important things for the week. One is, being a physicist, I have a slightly tilted way of seeing these things. I'm not your usual computer scientist, so you'll have to bear with me for a couple of hours. In particular, those scribes will take lecture notes. So for those of you, please come to me at any time. I'll be very interested in discussing with those taking notes, helping you proofread the notes. I happen to prepare a course for this, so if we can share, I'll be happy. And being a Belgian, on top of things, we have a slightly tilted way of seeing everything. So that's just normal. The second thing is just, it's a testimony to how important graphs have become in many, many applications. And I'll just start with a slide that shows, it's not even the breadth of potential things you can do with graphs these days. It's just a couple of these applications we've been dealing with in my lab. And so it's only a subset of it. You have many, many different things. So we've been working, for instance, on trying to understand energy networks. Well, graph is in the name, right? A graph, a network, it's roughly the same thing. You might be interested in wondering these days, in particular, how you can control an electrical grid where 99% of the power conversion is being done by renewables, for instance. So objects that are not on 24 hours a day and then cannot be switched on demand, because it depends on the weather. I've not worked on social networks, otherwise I would not be here. I would be a billionaire, most probably. But it's certainly a very interesting topic. So those of you who will join big companies like Meta and others, surely we'll have to play with kind of these networks on the right, where the nodes of the networks are users, and you're trying to understand. I guess politically, you're trying to understand how friends they are. In practice, you're just trying to understand how to sell them. Transportation networks is very important. That's the example in the middle. It just turns out that the Google Maps you use is now crucially using some of the algorithms we'll be introducing in the later stage of the lectures based on graph neural networks. Not for the whole system, of course. The whole system is a complex computer system, but the prediction and the estimation of ETA, so estimated time of arrival, when you select a destination, is now partly, to be completely honest, partly done using graph neural networks. But that's also an interesting problem at a smaller scale. Not everybody is Google. So if you want to be able to control the flow of traffic or the density of traffic at the level of community, for instance, you can, have GPS measurements and try to understand the traffic flow and maybe control it as well. We've been doing neuroscience, so a lot of people talk these days about neural networks, but these are the real neural networks here. Those you use really every day. And again, there's interesting experiments there where you can overlay the structural network of your brain, the one that is measured using MRI, or DT-MRI, for instance, and the functional activities of those regions. And so that gives a fairly complex signal that is overlaid on top of a fairly complex network. And you're interested in understanding things like, can I understand which part of the brain is activated and how it's activated, give tasks a user is asked to do? Or even maybe more interesting, can you predict the onset of some diseases by just looking at these activation patterns? That's very interesting. In biology, which is a domain which occupied me a lot over the last 2 years, there's a lot of graphs. So if you have a keen interest in biology, maybe some of you are biologists in the room, I don't know. It's a fantastic domain, extremely complex, very, very messy, with lots and lots of data. So here is just an example. This is the gene interaction network of yeast, where you see that genes are linked together. They are linked together when they are, one gene is a regulator of another one gene can be a promoter of another one, or a gene can code for a protein, which is an enzyme for a chemical reaction that starts with a protein of another gene. So all these interactions are extremely important and very, very complex. And basically, all your cells depend on the orchestration of these interactions. Since there are 20,000 gene coding proteins in any cell, you can imagine that. So it's not a very big network in the sense of not as big as Facebook, but it's extremely active. And the network changes with time, of course, because it's not like a gene interacts with another gene all the time. So this can change based on the stress of your cell, the presence of metabolites. So it's also evolving with. But there are maybe simpler applications, like here is a point cloud or a mesh. So if you do computer graphics, you're used to dealing with objects that are graphs and processing them, simplifying the mesh, trying to classify meshes, editing the mesh, or editing attributes over the mesh, color, the texture. In chemistry and in the frontier between chemistry and biology is extremely active these days. So there's a lot of interesting PhD thesis and research to be done in looking at the chemistry and the physics of molecules, and in particular their dynamics. And these days, there's many ways, but there's two important ways of linking graphs and molecules. One is to look at some surface properties of molecules. So this would be the electrostatic potential of a protein, a fairly large molecule. You're not seeing the atoms, you're seeing a particular equipotential surface around the molecule itself. But that surface is important because these molecules, they interact, let's say, essentially by contact. And so the shape of this surface and its local attributes, how it's charged, how it's discharged, this will tell you how those molecules interact. But there is another way of looking at molecules, which is sort of the traditional way, it's sometimes called the Smiles representation, where you see the atoms and the various bonds. And again, this is a network in the sense that the various atoms on these molecules are linked together. So there are nodes linked together inside the network. There are several types of links, like monovalent or bivalent bonds, for instance. But they can also change with, well, not with time, but these molecules have symmetries, and those links are not static. So there are equilibrium points where these links can fluctuate. And I had a joke with this molecule, but now I realize that I don't really remember the name of the molecule. It just so happens that this is an essential oil whose name I completely forgot, but who happens to be present in pastilles. This is my tribute to the place. Okay, so if you look at that, you see that, and you say, oh, it's tremendously interesting for very deep science, and I can solve extremely profound scientific challenges. Well, the real thing is that, of course. The vast majority of graph-based challenges you face in the industry is just due to the fact that we agglomerate an ungodly and frankly sometimes stupid amount of data by using services. And those who use these graph-based methods are those who have to deal with this data. So you will have to choose if you want to do that or if you want to do that. If you go working in industry, most of the time, it's a little less beautifully scientific than the brain neural networks, and it comes with its set of challenges, the first of which being the scale. And the methods I will present during the lectures, a lot of them have problems scaling to these kind of objects. So this also explains why in university, particularly in my lab, we have to focus on that because we don't have the infrastructure to focus on it. Okay, so that was a way of introduction. Graphs are very important, many applications. And for the few hours we'll spend together, I wanted to specifically focus, we don't have a whole semester together, specifically focus on a particular kind of use of graph in machine learning, which is sometimes called graph representation learning. And the reason why this is getting important is that, okay, if I have to schematically summarize machine learning into a single equation, that would be this one. You may agree or disagree, but essentially you want a system, it's a mathematical system in which you will input some data, something will happen, and we will be talking about the thing at large during this week, and it outputs a decision. And What you're going to do is that you're going to expose your system to pairs, data, decisions, parameterize this function or this operator f, and tries that in average with some well-calibrated loss function, it does its job. And not so long ago, at least when I was myself a PhD student, this basically involves this kind of architecture. Right? So you had a first step, which is here, where someone like me would handcraft features. So you would give me data, you would tell me the whole story about them, whether it comes from biology, from energy network, or other things. And I would, using domain knowledge, try to come up with algorithms or ways to extract features from the data. So I would not learn the features in the sense of modern machine learning. I would learn them with my own brain. Okay? And I would just try to come up with methods to give you numerical features. Of course, it's an oversimplification because, as you will see, we were able to design sort of universal algorithms to extract features in fairly generic ways. But the key message here is that this first layer of feature extraction was not learned. Fixed once and for all. And then, once those features are extracted, you just cross your fingers that they are good enough, and you throw them into a classical machine learning system, whether to do regression or classification, whatever you want. And that, of course, that last layer itself then is machine learning. Learn from exposing your system to a data. But lately, things have changed, and we've moved to systems like this one, where you typically have a feature extraction layer. You can see that it's much more complex than the ones I was used to design when I was younger, in the sense that there are composed layers of feature extraction. So they can get fairly complicated. That's what they are called deep architectures. And that those feature layers themselves are learned from data. So instead of handcrafting feature, you're trying to train the whole system, not necessarily end-to-end, as I will show you, so not necessarily taking the decision into account, but you're trying to train the whole system so that it will itself learn to pick up features. So when I say end-to-end, what I will mean is that you train the whole thing so that the features you extract there are trained jointly with the decision process. But you might just, for a second, just forget this one and try to train features in some sort of a universal way, irrespective of the end start. So find good features for the type of data you're dealing with. So good features are good representations of the data, in this case, and that's why I use the term graph representation. So for us, we'll be looking at these two things, because there was a natural progression from here. So the first lectures will be focused on that, and then contemplating the shortcomings of these things, we will move. Right? Good. And to be more precise about what we'll be doing this week, this is a short visual outline of our lectures. So we will start in the realm of constructing features, so using things we know about the data. So in our case, we'll be working on graphs. So we will start by explaining a little bit what we mean by these graphs and networks. Some of you already know. I gather that some don't necessarily have this kind of background, so we'll be going slowly there. And then we will go through some very well-known and not necessarily state-of-the-art algorithms like spectral clustering, just because it's a pedagogical tool to understand what's going on. And this will lead us to something that Remy alluded to in the introduction called graph signal processing. So the first few lectures will be about introduction to graph, using those methods to come up with algorithms that perform certain tasks, spectral clustering, Laplacian eigenmaps, graph representations. We will quickly just mention this series of algorithms. Then we will move to graph signal processing. So we will learn a set of principal tools to construct features in an agnostic way. Construct, not learn, but still in an agnostic way with respect to the task. These will include the equivalent of filtering and constructing wavelets. And then we will move in the last part of the week to architectures where you just train a feature extractor. When you work with graph, these are these days called graph neural networks. of which there are many flavors. So we will use our background to construct what was the first computationally efficient architecture called graph convolutional nets. We will also use the background we've learned here to modify them into message passing algorithms. We will classify the various types of message passing algorithms. And then we will try to study how powerful they are, maybe from a more theoretical point of view. And then we will have to come to a conclusion on their power, see that it has limitations, and then I will finish this week by talking about architectures that go beyond these traditional ways. So that's the... And of course, you never make it. I'll do my best. Okay, so typical tasks that we will be facing in applications will be, for instance, classifying nodes of a network. So here are examples here where we've come up with a coloring or a classification of each node, depending on what you want to do with it. For instance, in this particular network, the nodes were classified based on their structure in the graph. They play a particular kind of role, and the number of roles depends on the local structure of the graph. This gives you already the hint that whatever you do with networks, you will have to have tools that are able to see locally up to globally the structure of the graph. And the graph is a complex object. Sometimes it can be very messy. Another, maybe more applied thing is here in biological networks, where you're going to try to associate a node to, for instance, a set of genes, depending on what kind of process they regulate. Trying to learn the role of a particular network. This is coming from friends at Twitter, where they color users in the Twitter network, a set of the Twitter network, depending on how you should trust them for a particular topic. This was their ultimately futile attempt at stopping the propagation of fake news. It just didn't work, but it led to a nice algorithm. So that's when you want to deal with nodes. Another potential task would be to deal with a subgraph or the whole graph itself, classifying them. So here, in this application we did in my lab, the goal was to classify parts of a graph. This is a protein surface, to try to understand where another molecule would dock. So there you have to characterize not just the node, but its whole neighborhood, a patch, if you wish, in the graph, based on a data set, trying to find a way to train a feature extractor that would tell you exactly where some type of molecule would attach to this. A graph-wide application of this would be here, where you color nodes based on their belonging to a particular community in the network. You can see with your bare eyes here, because I have laid out the graph easily, that you can split this network in two. This just happens to be political communities. And there you're interested in being able to detect and classify those kind of things. And then maybe the more generic application would be, instead of looking at the graphs or constituents of the graphs, you have a field of attributes defined over the network, either defined over nodes or edges, or for the whole graph itself. And what you're trying to do is, well, classify that as a field of features. So you may want to understand, for instance, the time evolution of traffic flow over a network. You may want to be able to classify a whole network in a family of networks. And you can do that with. Okay. Right, so we will start this morning with a few elements of graph theory, and in particular, because graph theory is a very, very, very big topic, I will focus on only a subset of it, which I will use throughout the lectures as sort of a red line to guide us, which is spectral graph theory. And for those of you taking notes, it's all in this nice little book by Fan Chung called Spectral Graph Theory. Okay? And I think I have the PDFs on my laptop, so that can help with the note taking. Okay, so in most of the applications and architectures I will consider during this week, we will be working with what's called an undirected graph. Okay, so I will make this definition clear. But certainly a sizable fraction of what we'll be doing is valid for arbitrary graphs where there is a notion of direction. So for us, what will be a graph? It will be a set of nodes, of vertices. It will always be a finite set here. They will be linked by edges. I'll define the edges, but there's a finite list of edges. An edge is a relationship between nodes. And we will summarize most, if not all, of the properties of the graphs inside very simple to understand matrices. So for instance, you can look at how much a particular vertex is connected, so how many edges are attached to this vertex. That would be called the degree of the vertex. And you can stack all these degrees into a diagonal matrix that will be called the degree matrix. That will be just a simple algebraic object that tells you how the list of nodes and how well connected they are in the net. You could be more precise and split those degrees into degrees related to edges that point to the node, so in degrees, and degrees connected to edges that go out of the node, out degree. So you will have to do that if you consider a directed network. For an undirected one, there is no distinction. This simple object will do that. I'll talk a little bit more about this object in a second, but this is yet another example of a matrix we'll be doing. So the incidence matrix, it basically summarizes everything you have to know about the graph. So this is a fairly big matrix, which has nodes in one dimension and edges in the other. And it basically tells you in position ij, if there is a +1, it simply means that there is an edge linking node I. So edge j links node I to some node k. So there's an edge that leaves node I. And by convention, if it leaves node I, I'll put a +1. And then if it's an edge that comes to node I, then I'll put a -1. So this is an object that allows you to deal with any graph, directed or undirected. What if the graph is undirected? There is no edge that leaves or comes, so that you just don't care about the sign. As you will see, you can just choose the sign at random, and they will disappear in what we'll do. Okay. Good. Now, the most celebrated algebraic object for studying graph is called the adjacency matrix. The adjacency matrix I will denote by this bold A. Simply tells you, well, in the case of an undirected graph, A at position ij will be +1 if there is a relation between I and j. Again, you have to pay attention. Is your graph directed or undirected? If it's undirected, the matrix will be completely symmetric, because I being linked to j means j is being linked to I. In the case the graph is directed, there might be a link from I to j, but no link from j to I. Okay, so we just pay attention. Right? Almost done with questions. Sometimes, and very often in the applications we will see, the connections between vertices is not just binary. The connection can be modulated by a strength. So two nodes can be linked, but with a different strength of connection. So in this case, you will model that by using not just the pure adjacency matrix, not just the pattern of connection, but taking care of the strength of the connections using what we could call a weight matrix. So this has the same dimension and shape as the adjacency matrix, but W in position ij, which will tell you not just that the two nodes are linked, but how strongly linked they are. In the majority of the literature, those connections you will consider non-negative. So it's really the idea of a strength. There are applications where you have to go past that. There can be negative connections. If you look at correlation work, we don't have 2 full weeks, so I'll just focus on this particular type of weight. And again, if there is a notion of strength of connection, you can modulate the degree of a vertex by taking into account the strength of the connections to that vertex. So instead of summing the j-fline of the adjacency matrix, the i-fline of the adjacency matrix, you will sum the i-fline of the weight. Summing all connected strengths gives you an idea of how strongly connected a particular node is inside. Okay, good. Now, let me come back to my matrix S, this incidence matrix. If you remember, it's a node times edges. I can transpose it and multiply these two objects together. So S times S transpose gives you a matrix which is extremely famous and gave its name to the whole mathematical field of spectral graph theory, called the Laplacian, or the normalized Laplacian of the graph. I'll come back to that particular definition afterwards, but maybe it's more intuitive to see this one. So you take two matrices we've already worked with. Consider an undirected graph and with no connections. So you just have the regular degree matrix and the adjacency matrix. And both of them are symmetric. So you construct this matrix L by taking the difference of the degree minus the adjacency. So this is a symmetric matrix. And as we will see, it has other properties. It's called the unnormalized Laplacian of the graph for various reasons. One of them, we'll see several of them, but one of them is fairly intuitive. We can look at what this matrix is doing if you apply it to a vector. So take d minus a, pick up a vector that has the size of the number of vertices. This is number of vertices times number of vertices. And apply L to that vector. And now look exactly at what happens at a particular component of the output. You will see that what it does is that it takes, so if you look at component I, it looks at vertex number I. It will multiply it by its degree. Then it will look at all vertices that are connected to I, because that is one line of the matrix A. It will multiply the entries of those vertices by 1, if there is no strength in the adjacency, and you will take the difference of that. So it's like you're sitting at vertex I, you're looking at your neighbors, and you're taking differences of the value at I, multiplied, rescaled by the degree, minus the value at your neighbor. And if you think of it, it's kind of taking some sort of isotropic derivative around the vertex. It's looking at your value, it's looking at the average of your neighbors and taking a difference. Okay? And hence the name Laplacian. If you write the Laplacian matrix down for some very fixed network, like a grid, you will also see that the matrix, we will see it, looks like the discrete second derivative. It's another way to understand why it's called. If the graph happens to be weighted, so if there is a connection strength, you'll do a simple substitution of the matrix D and the matrix A by the weighted object. So L is symmetric by definition. It's also a positive semi-definite matrix, which you can easily prove by again doing this little experience of acting on it on a vector. So if you just literally compute X transpose Lx for any vector X, and I did it here for a weighted graph, out will come this formula almost immediately. So this formula is a lot of very interesting features. The first and basic one is, yes, indeed, it's telling you that L is a positive semi-definite matrix, because all these guys are positive here. It's also revealing the differential nature of L, because you see those discrete differences between X, I, okay? And if you look at, and weighted by the strength, so you do take into account the local structure of the graph when you compute these differences. But it's also giving you an idea. So if you think of X as being an attribute defined over nodes of the network, like how much traffic there is at a particular position in a traffic network, or how much activity there is in a particular area of your brain, that object here tells you how smooth this information varies as you move over the network. Why? Because if X at position I is very different than X at position J, and these are linked in the network, this difference here will be big. So wherever two strongly connected nodes have attributes that are very, very different, they will contribute very strongly to this sum. If everywhere in your network you can have a field of attributes that changes from node to node, but in such a way as to make this sum very small. You would just have to have attributes I and J close together if they are strongly connected. So this gives you also, at least for me, an intuitive way of something that's sometimes called homophily. The fact that over many, many networks, the attribute or the information that you overlay at a node is usually very strongly related, very close to the attributes of nodes that are themselves strongly connected to the node you are looking at. So information doesn't vary too much as you move from a node to a strongly connected node. This is a strong hypothesis. You could construct networks in an arbitrary way where you violate this. But in many, many natural networks, that will be the case. And there's also ways to construct networks just based on information, just based on the axis, in such a way that you will guarantee this. So this is it's a sort of simple and trivial, but very, very important topic. Okay. Oh, and I used X as a scalar, but you could imagine that you do it dimension by dimension of a non-scalar attribute. So this carries over to vector values. Right. Okay, let me go back to this matrix S. Because in the guise of a purely algebraic object, it's actually some sort of a differential geometric object in this guise. So I'll remind you of the definition of this matrix S. And if you look at it, picture yourself this configuration in the network where you have a node I, a node K, and the edge going from I to K is just labeled J. So the fact that this edge is present and goes from I to K means that at the JF column of the matrix S, I will have a +1 in position I and a -1 in position. Right. Now, let's do a quick calculation. So again, let's take a field of attributes over the network. So think of a scalar defined at every node, just like we did before. And take the matrix S, transpose, and apply it to F. You take a vector that has the size of the set of nodes, you apply the matrix S transpose. And if you use the definition literally, you will get that S transpose F at position J is just the finite difference Fi minus Fk. Remember that J is this edge. All right? So it will be a set of finite differences indexed by the edges. In this guise, so if you collect all these finite differences, you see that S transpose maps information from the nodes to information defined on the edges that linked those nodes. So if you have an attribute field over the nodes, over the vertices, if you apply S transpose, you transform that into an attribute field that is now defined on the edges of the network. And this object is called, well, it's a collection of finite differences, so a good name for it is the gradient. The gradient of a scalar function is a vector field. We don't have something like a vector field over a network, but we have objects that look like directions. These are the directed edges. And so this plays the role of the gradient operator as computing derivatives in direction. Now you can do the converse. Take now, that's why the capital letter is here, take a field of attributes defined over the edges now. So you imagine you have a network, and at each edge, you have an attribute saying, I don't know, what type of edge this can be a label. And now you're going to apply S to that particular attribute field. So G is a function that lives over the edge set, and S takes from edges back to nodes. And the way it does that is also by taking differences of the attributes of two edges if and only if they share a node in common. It goes from edges back to nodes in a differential way, in a finite differential way. And so its name is the divergence of the edge signal. So now you have two operators, S transpose and S, the gradient mapped from nodes to edges. The divergence maps from edges to nodes. And again, we go back to a good reason why our matrix is called the Laplacian. If you take the divergence of the gradient in differential calculus, you get the Laplacian and you get the same proof. All right? So this basically tells you a few interesting things. One is that maybe there is a connection between these simple objects we have defined. Right now, we've just defined a couple of very simple matrices, but in such a way that there seems to be a connection with differential calculus. So maybe we could go that way. Okay, and it's interesting. Another thing this tells you is that, okay, we've done one step. We've gone from nodes to edges using the gradient, and then we've came back. But maybe we can go to more complex structure. For instance, we can go from node to edges, and then what comes after edges in a network? Triangles, for instance. Yes. So can I use the board? So I have a sideboard. Oh. So if you have three nodes linked by edges, you can go from information at the nodes to information at the edges. But then if these nodes, if these edges are closed and form a triangle, you could pull out the action, the information defined at the edges into an information defined on the triangle. And so you could then wonder, is there something in a network? Is there something beyond triangles? So can I take triangles that are congruent and have an operator that will differentially map to a higher level structure? And the answer, as we will see at the end of the week, is yes, indeed, it's true. And it's completely reminiscent of the same construction you do in topology. And so you can construct from a simple network gradually more complex discrete topological objects called simplicial complexes, where you will gradually map information to finer and finer topological structures. And this will give you a way to describe a graph in increasingly more complex way, but also increasingly more distinctive way. And when we will have to go past neural networks, maybe this will be. Okay. Good. So let's go back to the graph Laplacian. The graph Laplacian has a lot of properties that are reminiscent. So it has algebraic properties, which all mean something about the network. This is why it's so interesting. It's a very simple matrix. You can study it. And whatever statement you will do about this matrix will automatically turn out about a statement about the graph. That's very interesting. So, and you will see that these statements are very simple. So first of all, it's a real symmetric PSD matrix. So the simplest thing you can do to such an object is take its eigendecomposition and look at its eigenvalues and eigenvectors. So if you do so, you will immediately see a couple of interesting things. Well, first of all, since it's PSD, all the eigenvalues are non-negative, so that doesn't depend on the fact this is a network. But if you order them in increasing order, the first eigenvalue will always be 0. The first eigenvalue of the Laplacian will always be 0. And it's easy to see, indeed, that if you apply the Laplacian to a constant vector, you will get 0 because it's a differential object. It computes derivatives. So if you compute the derivatives of a constant, you'll get 0. Now, that's trivial, but can we learn something maybe more structured from this decomposition? So first of all, let's look at examples, and then we will look at the map. Okay, let's take a path graph. So a path graph would be something like this. So a set of nodes, imagine them in one dimension, just connected in this way with no direction. Okay, and it's finite, and the start and last node are dangling. So if you look at the adjacency and the degree matrix and construct the Laplacian, you will see a very structured matrix like this one, which you have seen if you have done finite elements. Okay, so this one is no surprise. Now, if you look at the eigendecomposition of that, you can do it by hand because of the nice symmetries. And you will see that you have an expression for the eigenvalues, but more importantly, that you have an expression for the eigenvectors. And if you look at these eigenvectors, you see cosines of increasing frequency. The frequency increases with the eigenvalue. And these, by the spectral theorem, form an orthonormal basis. And it's an orthonormal basis that a lot of people know under the name DCT2 transform, the discrete cosine. That's the one that is used in particular if you do JPEG. So people who do signal processing are used to using these vectors without ever caring about the object that they come from. You can modify a little bit of network if you want to do an exercise. You can make a connection between the first and the last vertex. And what you obtain is a ring. Okay, on a ring graph, the eigenvalues will change slightly, but still be ordered in increasing progression. And you will have pairs of eigenvectors that are, again, trigonometric functions, or sines, cosines, of increasing frequency. And again, that's the DCT, well, DCT1, I believe, the DCT1. So a very well-known orthogonal transform. So why did I do this exercise? Well, first of all, because you recover objects that come from completely different fields, but also because it signals that the eigenvectors of the Laplacian matrix may be very useful to do stuff. Like the DCT is very useful to do signal processing. Can, in general, in situations that are much less symmetric than that, can we use these eigenvectors to also do stuff? That would be a very interesting question. And what kind of stuff and what kind of control do we have? Okay, so let's go on and explore these properties. One very important concept is that the eigendecomposition of the Laplacian reveals the connectedness of the network. The proposition goes as follows. The number of connected components of the network, so the number of connected components is subgraphs of a graph that are not connected together. Right? It's a connected subset, another connected subset, but they are not connected together. So like your graph is a union of disjoint subgraphs that are not connected. They do not share a network. Now, interestingly, the multiplicity of the first eigenvalue of the Laplacian is always equal to the number of connected components of the Laplacian. So by just looking at the zeroth eigenvalue and its multiplicity, you immediately get a simple test to check if your network is connected, and also how many disconnected components it's going to have. Even better than that, if you now look at the eigenvectors, so if there are disconnected components, the first eigenvalue, the eigenvalue 0, has some non-trivial multiplicity. So that's the null space of the Laplacian. I can always choose a basis in that subspace, and these will be eigenvectors of L. So I have freedom in choosing these bases. And I can choose a particular basis that is very revealing. I can choose a basis of indicator subset of each component of the network. So if I take a vector x, which is going to color the nodes with, let's say, color 1 if the node belongs to component h and 0 elsewhere, so it's like an indicator of a component, that is an eigenvector of eigenvalue 0. Which basically means that eigenvectors of the 0th component of the Laplacian will not only, the eigenvalues will count the communities, or will count the disconnected subsets, but the eigenvectors will label them for you. We tell you this is component 1, this is component 2, this is component 3, whatever the order. Give you a coloring into this disjoint union of subnets. So that's interesting. Let me. Okay. Now, what happens if, instead of being so dramatic and having disconnected components, I start drawing edges in between these components? So I start with disconnected components, let's say 2 of them. So the first eigenvalue is 0 with multiplicity 2. And then I will slowly rewire the graph by making connections between these 2 at first disconnected components. If you do that, so you can do a little numerical test. You generate at random 2 subgraphs, disconnected, and then you at random start drawing edges between these 2 components. And you look at lambda 2. Lambda 1 will always be 0, because this is always the case. Now you start looking at lambda 2. At first, when there is no connection, lambda 2 is 0 as well. But then as the graph will get connected, lambda 2 will increase. It will, as soon as there is a connection, it will be non-zero. But what's interesting is that it gracefully increases as you increase the connectivity of the 2 components. Okay, so it's not like it jumps widely from 0 to another value. It will smoothly increase as you increase the number of connections. And in fact, you can prove a lower bound on lambda 2, which depends on this object, which is the diameter of the graph. The diameter of the graph is the following thing. You take any 2 nodes, and you look at all the paths going from node I to node J. Among those paths, you take the shortest one. You take the shortest path from node I to node J. And then you look at what is the longest possible shortest path in your network. So you look for the pair of nodes such that the shortest path between these 2 nodes is the longest among any pairs of vertices in your network. So this tells you how large your network is. Intuitively, if there is a very strongly connected set of nodes here, a very strongly connected set of nodes here, and if you have just one edge going from here to here, there will be lots of paths walking inside this component, then going here, and then going here. So there will be very long paths from a node here to a node here. If there is no connection, there is no path between a node here and the node here. So it's like the diameter of the graph, if you wish, could be infinite. Okay? So if you keep adding connections, you are decreasing the length of the shortest path. And what happens is what you see in this equation. For a graph that is very, very large, with large shortest path, lambda 2 is going to be going down. And at the limit, when there will be disconnectedness, d will be infinity, so lambda 2 will go to 0. But as you keep increasing the connections between components in your network, the diameter will go down, and lambda 2 will then increase. If you take a social network, for instance, you may have seen a lot of these headlines, like the diameter of Facebook. So the number of connections between you and anyone else on Facebook is like, what is it, 5, 6, right? It's an old experiment that was done in the 19th century by sending letters. Saying how many letters you have to send from one person to another, so that if I start, my letter will end up to the Pope. And it was 7, I believe, in the old physical, so the 7 degrees of separation. And then with Facebook, we just shortened that just a little. But so what we have to get from here is that as you go a little finer into the analysis of these eigenvalues, and as we will see the eigenvectors, you get more and more fine-grained information about what's going on in the network. You start it with there are disconnected components, then where they are, and so even if there are connected components, you get here an idea that you can understand how strongly connected 2 components in the network. And that starts to be very interesting now. Because if you have networks where we have communities of people interacting together, or communities of genes interacting together, but with cross-interaction, what we might be interested to do is, can we detect these communities? Can I come up with a simple algorithm that will automatically, however complex is the graph, tell me that there are communities, so groups, subset of nodes that are strongly linked together and only loosely linked across. So that's an interesting algorithm. There's a lot of applications where we might want to do that. Community detection in social network, module detection in gene expression, patterns of congestions on a transportation network, patterns of congestion on an electrical grid. So being able to detect these kind of communities is very interesting. And we are not very far from there, because we see that spectral analysis is telling us whether there are these kind of objects, and maybe even a way to detect. So let's go a little further. Yes? The volume there is just a constant. You can take it as the cardinality of the set of. It just plays that role. Okay, so we can go one step further and make this even more precise, and this will lead us to the first algorithm. So what we need is not just a way to measure connectedness, but a way to measure the strength of how two subgraphs are connected together. And what we will be looking for, what we wish to accomplish, is to be able to find when in a network there is some sort of a bottleneck. So you could picture two strongly connected components, and in between these components, like a bottleneck of edges going from one component to the other. Okay? If we can have a simple way to characterize the presence of these things, and then a simple algorithm to detect them, we would have solved an interesting problem, which is partitioning a network into communities. All right. So let's first look at the mathematical description, and then we will look at the algorithm. There's many ways of doing it. One way is to look at what's called Cheeger constants, and I will make them graphic in a second. But the Cheeger constant is really trying to summarize my little drawing. So you look at a subset of nodes, say A, included in the set of nodes. We will define its boundary. The boundary of a set of nodes is simply those edges that live or that go across the subset A. So one node in the edge must be in A, and the other node of that edge must be in the complementary set A in V. So in my little drawing here, these would be those edges. I should have defined the volume before, but here it is now. The volume of A will simply be the sum of the strength of the edges in. So I can define the volume for any set. For instance, I could now define the volume of those edges that go in between two regions. And then you see me coming as big as a truck. I would like to identify these bottlenecks and how strong they are. So this will be a constant. That's one of the ways of defining Cheeger constants. We will do the following. We will look at, for a given set, A, a given set of nodes, we will look at the cardinality of the boundary of A. So how many edges go out of A. And then we will normalize that by the size, the size, a good size. So a good size would be minimized by the size of A or the size of its complementary, because we don't want to have extremely small set of nodes. So we're going to try to make this balance. And so we are going to look for a set of nodes A in V that minimizes this thing. So if you look at what this is trying to do, it's going to have something that has a small boundary, but with a rather big volume. Okay? And that's almost the mathematical definition of my graphic here. Or maybe if I pull it out here, yes, it's there. So this will be particularly characterizing bottlenecks in between two subsets of nodes. So for instance, here you have a community of nodes that is strongly connected. Here another subset of nodes that are strongly connected in between. And then you have few strong edges that go in between. So that's a bottleneck. That's an element for which the Cheeger constant will be valuable. Okay, now that's just math. It didn't tell us how to find these two. Just a way to mathematically characterize its appearance. Okay. For those of you interested in digging deeper, there's a vast literature on computing these Cheeger constants for various types of graphs. We're not going to do that. But if you have a keen interest in graph theory, you could wonder, what kind of model, what kind of type of graph will lead to a small Cheeger constant? Or another interesting question would be this one. Is there a relationship between the Cheeger constant and the eigenvalues of the Laplacian? And unsurprisingly, there is. In fact, there are many relationships. And you will not be surprised to see this particular equation, because we already saw intuitively that lambda 2 measures the connectedness in between regions in the graph. So since h of g measures the presence of bottleneck, it's unsurprising to see that the Cheeger constants, this is one of the loose such inequalities. There are much finer ones for more precise type of graphs. But for any graphs, it's unsurprising to see that if indeed there is a small Cheeger constant, it will force your lambda 2. And so from now on, we have to keep in the back of our mind that playing with the Cheeger constant or playing with lambda 2 is almost the same thing, with the difference that computing lambda 2 is much easier. Okay, and we will play with it. Okay, so well, I don't know of any algorithm that is not just sweeping through a subset. But maybe computer scientists in the room know of. But for an arbitrary graph, I don't know of an algorithm that does it without sweeping through. The algorithm we will see almost does that. You could do a variation of ratio cut. We'll see afterwards. But then you have to relax them to get that is not exponential in the number of. Well, this is a yes. Okay. Before going to the algorithm, because it's already 10:50, let's motivate ourselves with the fact that if we do the effort, we will get something valuable. So, I told you that lambda 2 reveals the presence of these bridges in between communities. So, if this lambda 2 is different than 0, you're strongly suspecting that there are communities in your network with bridges among them. The corresponding object to lambda 2 is the eigenvector u2. Let's just have a look at the eigenvector. Let's not do any math, let's just have a look. So I take here, this example here is a set of political blogs in the US. Since it's a two-party system, there are Democrats and Republicans. And each blog is linked to another blog if and only if, in a window of time, there was on the blog a link to an article in another one. So it's a citation network. So you look at all those blogs and whether they cite each other. Intuitively and unsurprisingly, the Democrat blogs cite a lot of Democrats, the Republican blogs cite a lot of Republicans, and from time to time, there is like a centrist kind of blog that cites a centrist kind of blog, or maybe a Democrat will cite a Republican just to say, oh, look how crazy they are. Okay? But most of the links will be inside the political community. Now, what I did there is I computed the Laplacian, I computed its spectral decomposition, and what I plot here, forget the right, what I plot here on the left is the sign of the second eigenvector. So I take u2 of I, and I look at the sign of that. So that's plus or minus 1 for any node. And I just show it to you. And what you see is that, well, it does indeed seem to partition the network into two components. Well, this is plus 1 or minus 1 is, of course, arbitrary. And if you now overlay the ground truth in this case would be how these blocks self-declared themselves in terms of political leaning, well, you see that you are very, very close to having found a very meaningful part. There's a few nodes that are misclassified, but political obedience is not mathematics. So maybe we should not expect perfect recovery in this case. Okay, so, yes. Oh, well, I didn't explain how I plot this. So in order to show you the graph, I projected it in 2 dimensions. the way I projected the graph into dimension will be the subject of what I'm going to say in the next. Okay? But now, for a second, I just have a simple way to map a network in the plane so that you can look at it. Okay. Yeah, that was not very pedagogical. All right. And then just before the break, because we need a little bit of suspense, we'll do the algorithm before the break. Let's delight ourselves by looking at those eigenvectors for increasing lambda. So here is a fairly complex network. It's a road network of the state of Minnesota, I believe. So every node is an intersection in the road network, and they are linked if there is a road going from an intersection to another. So this is the first eigenvector. So I'm just, again, looking at the value of the components of the eigenvector, not just their sign. So the first eigenvector is a constant. That we already know. The graph is connected. So the second eigenvalue is not 0. It corresponds to an eigenvector. And this eigenvector has a polarity. It must be orthogonal to constant. Wait, before the break. It must be orthogonal to the constant. That we know. But it could still be oscillating all over the place. So why is it so nicely organized? I mean, I can come up with zillions of ways to make a pattern of values here orthogonal to that. So why on earth is there some sort of organization in this? Why is it smoothly changing as I move over the net? That's important. Remember, we're looking at eigenvectors, and remember that object. So finding eigenvectors could also mean looking at the decomposition of this, okay? And to each eigenvector, there will correspond similar object. And we know that the eigenvectors are the ones that are going to minimize, the eigenvalues are the ones that are going to minimize this quantity. But this quantity we already know, it tells us, so L ui is going to be very small if the values of ui over connected nodes are very close to each other. So for the first few eigenvectors, the first one will be, that will be 0. For the first non-trivial eigenvector, that must be the smallest possible non-zero. So the way ui components vary from node to connected nodes must be extremely smooth. Otherwise, this will be big. And so this explains why you get this kind of nicely organized, smooth varying oscillation over the network. And then the next eigenvector must be orthogonal to these two, but still smooth enough. So it cannot do anything. So it has to oscillate in another direction. And you see these oscillations progressively increasing. Why is it interesting? I showed you the example of the DCT for a very regular graph. But you see that you get this idea of nicely oscillating components even for a very complex graph. Well, this one is very, very complex, but at least it's not great. And so the organization of these eigenvectors, even though I cannot compute them by hand, is revealing some of the structure of the underlying network. And we've already seen that this guy is going to relieve partitions into communities when they are. We will do that more precisely in 10.